Heyo, gamer with taste here, and today I want to talk a little bit about the Mandelbrot set. So I have the whiteboard here with me. We're gonna go over a little bit of information about the Mandelbrot set. So let's get right into it. So the first thing that you need to know is this is what the Mandelbrot set kind of looks like. Okay. So, I mean, this is just kind of what it looks like. Now, you'll see that it's a little bit of a sideways heart with a whole bunch of circles attached to it. Now, these circles aren't perfect circles in all actuality. If you want to get a good look at the Mandelbrot set, just look it up on Google. Just search Mandelbrot set. You will not be disappointed, I promise you. It's really interesting. If you choose a Mandelbrot set viewer, it'll let you zoom in, and you want to zoom in close to the Mandelbrot set. You don't want to zoom in like right here or right here. You want to zoom in like on the boundaries. And that's what looks interesting. Or on like a branch or something. That's what looks cool. But anyways, the Mandelbrot set is a set of complex numbers, which is basically anything that has a real component and an imaginary component, something like 1 plus I, something like that, right? It could be 14 plus I, it could be 20 plus 2I, it could be 70 minus negative 14i, but that wouldn't be simplified. But whatever, you get the idea. I'm not going to go into too much depth about what the Mandelbrot set is, per se, but it is a set of numbers. It's just a collection of numbers. It's a relatively small collection of numbers, but it's a very interesting one. So, what you need to know is that these circles, which aren't actually circles, but these things attached to the cardioid, these are called the bulbs, okay? So this one on this side, this is the 1/2 bulb, right? That's what this one is. And then this one, like, this isn't really a bulb. This is like the butt crack of the Mandelbrot set, right? Sorry to make it sound so unprofessional, but that little cusp of the cardioid, that is the 0/1 bulb. That's how I refer to it. I don't know if anyone else really refers to it as such, but it works for me. And mathematically, I think it works. So, anyways, that's the 0/1 bulb. This is the 1/2 bulb over here. So what you can do to find the biggest bulb in between any two bulbs on the cardioid, which the biggest bulb in between would be the one up top, the 1/3 bulb. So what you can do is you can fairy addition the fractions. So if I wanted to find the biggest bulb between the 1/2 and the 1/3, that would be the 2/5. So what I ended up doing is I just took 1 and I added the 1, right? 1 plus 1. And to get the 5, I just did 2 plus 3, right? So that's all you have to do. This fraction actually means something for each and every bulb. I believe the numerator, I don't want to spread misinformation. I believe I know what it means, but it's been a while since I've researched it, so I'm not going to tell you what it means because I don't want to spread misinformation. But this does mean something. So doing this with the fraction, that's called finding the mediant, right? So this is the mediant of the 1/2 and the 1/3. So if you want to find the median of the 1/2 and the 0, 1, then it would be 1 plus 0, which is 1, over 2 plus 1, which is 3. And sure enough, we find the 1/3 bulb located at the top. That's the biggest bulb in between the other two. And if we want to find the biggest bulb between the 1/3 and the 0, 1, then we just do 1 plus 0 and we get 1. And we do 3 plus 1 and we get 4. So that's the basics of the bulb information on the Mandelbrot set. But as I studied this, I've done some studying on this. I've approximated the area of many bulbs, not all of them. I mean, there's an infinite number of bulbs attached to this cardioid, right? Infinite. But I have really kind of noticed something during my studies. So first of all, each bulb is rational between 0 and 1. It's going to be rational. I mean, they're fractions. 1/2, 2/5, 1/3, 1/4, 0 over 1. I mean, down here, I think this is 2/3, right? These are just above 1/2. So it kind of goes between 0 to 1/2 and 1/2 to 1. But since it's symmetric across the real axis, I only really look at the top. I just feel like it's easier that way. But every bulb is going to be rational between 0 and 1. And I've noticed that the smallest bulbs converge to irrational numbers, which I'm pretty sure this is right. It may not be right all the time, because the thing is that obviously as you get smaller and smaller and smaller bulbs approaching the 1/2 bulb, I'm pretty sure you are converging upon 1/2, right? As you reach the smallest bulbs entering the cusp of the cardioid, you're obviously approaching 0. And same with 1/3, 1/4, 2/5. I mean, the thing is, though, is that you have the set of all rational numbers between 0 and 1 represented as a bulb on the cardioid. You have every single rational number represented here. All infinite of them, right? So, what you can do is you can choose an irrational number between 0 and 1, and you can use medians to converge upon that irrational number. That's what you can do. So to show this, right, I have chosen pi over 10. So pi over 10 is approximately 0.3141592653. So what you will do is you will start with the 0 over 1 bulb. You start with 0. And you mediant to the 1/3. You mediant with the 1/3 bulb, right? So you have 0 plus 1. That gives you 1. Then you have 1 plus 3. That gives you 4. So now you're at 1/4. And then you mediant with the 1/3 again. And so you have 1 plus 1, 2. 4 plus 3, 7. And then you mediant with 1/3 one more time. And you get 2 plus 1, 3. 7 plus 3, 10. And now you have 3/10. So you have reached the 3/10 bulb. So that's 0.3, right? That's where we got to. So now we're going to median with 14/45. So now we're finding the biggest bulb between the 3/10 bulb and the 14/45 bulb, right? Which is close to 1/3, but not quite. So we have 3 plus 14, that's 17. 10 plus 45, that's 55. And then we do the same thing over again. 17 plus 14, that's 31. 55 plus 45, that's 100. So now we have 31 100ths, 0.31. So now we have the 0.31 achieved, right? So now we have the 31 100ths bulb. And now we got a median with the 283 900ths bulb. So then we get this. And the process keeps on going. Eventually, you hit this one point of the process where you got a median with a specific fraction. Like we medianed with the 1/3 bulb 3 times, and then we found the median with the 14/45 bulb, like twice. But eventually you find this one that you have to median with 72 times in a row. And you might, if you're thinking about this really like quickly, you might be thinking, okay, well, I mean, you medianed with the 1/3 3 times. Why didn't you just median with like you could have medianed with the 3/9 bulb, right? You could have just added 3 and you could have just added 9. Why didn't you just median with the 3/9 bulb? Well, the 3/9 bulb is the 1/3 bulb. Like there's no 3/9 bulb located on the Mandelbrot set because 3/9 is an improper fraction. There's no improper fraction on the Mandelbrot set. So, yeah, I could have medianed with that fraction, but it simplifies to the 1/3. If we really want to median with the 3/9 bulb, we're gonna have, well, it wouldn't be a bulb, but if we want to median with 3/9, we have to median with 1/3 3 times. If, we're really looking in the context of the Mandelbrot set. Mathematically, I suppose we could do that. It's just, I don't know. Mediating with an improper fraction, like, it's still improper. You know what I mean? I don't know. In the context of the Mandelbrot set, it makes more sense why I chose the median with the 1/3 bulb 3 times in a row. But it makes it really difficult when you get to the point where you have to median with a specific fraction 72 times in a row. And that's literally just to get to the next approximation. Like we had to do 1/3 just to reach the first approximation. And that's not very good, right? Like that's only 0.3. And then we needed to do 2 more to get to the next approximation, so on and so forth. So it is one of those things where I'm not entirely sure what purpose or what, yeah, I don't know. But I'm still trying to figure out, like, the pattern with this. I think I may have kind of figured it out here. Just looking at it right now, I think I might be onto something more. But maybe not. I don't know. It's hard to say. It's actually really hard to say. Yeah, whatever. It doesn't matter. But yeah, this is the information I wanted to go over. So we can choose um a series of rational numbers. We can choose a series of bulbs, right? We have a whole set. We have every rational number between 0 and 1. And we can choose specific ones that will converge upon pi over 10. It is kind of interesting, though, how we converge to it because we get 1/4. Oh, wait, no, never mind. I was about to say something stupid, but I mean, I want to converge with numbers that are below it. Like 1/4 is below it, 3/10 is below it, 314 1,000ths is below it. So we're slowly climbing up and up and up, closer and closer and closer. So yeah, I'm kind of, I'm kind of, I don't know if this is already like written down somewhere. If someone else has already like thought of this, it's probably, honestly, it's something so simple. Like, I'm probably not the first person to have thought of it. But if you have the set of all rational numbers between like 0 and 1 for this context, right? You can choose a set of rational numbers with like a subset. You can choose a subset of rational numbers from that set between 0 and 1 to converge upon any irrational number between 0 and 1, which is kind of interesting, you know? And it's funny because, like, I say that the smallest bulbs converge to an irrational number because no bulb on the Mandelbrot set is going to be irrational. Like I said, though, like some of them converge to 1/2, some of them converge to 0. Not all of them will converge to an irrational, but honestly, you could probably make the argument that none of them converge to an irrational. But if that was the case, then why are we able to come up with a series that converges upon an irrational, right? Well, yeah, that might still, I don't know. I'm kind of rambling at this point. Maybe there is something to be said about that. Maybe they don't converge to an irrational, but you can choose a series of them that will. In any case, thank you for watching. This was just uh this was just me going on about what I've been looking at. So, if you enjoyed, then like, comment, subscribe, I guess. If you like cats, I do cat stuff. I do cat content. But anyways, thanks for watching. Hope you have a good one. Hope you continue having good ones. And I hope to catch you on the next video, whenever that is. Whatever kind of video that is. But until the next time, I'm going to have to catch you later. Take care.